Talk in a little bit more detail now about a charged particle moving through a constant magnetic field. So what we're going to have is this. I'm going to change my coordinates around a little bit here. I've got x, y, so z is going in this direction. Okay, and I've got a magnetic field that goes in that direction. Actually, I was thinking about that when I flipped this video. So you guys can actually see what I'm writing. I'm wondering if this direction changes as well. So my hand motions might not coordinate with what you see on what you see drawn, but I think it's still consistent. Okay, so let's now go ahead and take our charged particle that has a charge q. So here's our charged particle with charge q. Let's go ahead and give it some arbitrary velocity. So let's go ahead and just give it some velocity in this direction, and this is what we're going to do. We are going to define this angle as theta, the angle from the x-axis down towards the y-axis. We're defining that as theta, and then we want to find what our x and y components of this are. So let's just go ahead and say we have a v0, and so our x and y our v is simply going to be equal to v0 cosine theta I hat plus v0 sine theta j hat. Okay, so all we're doing is we're taking the original result we had for when we use the right-hand rule and when we use the determinant form of calculating the cross product of v cross b. We're now making that v, we're giving us the flexibility to have this be at different angles. And this is good because what this will do is allows us to look at things over time. Because you'll remember once we had that force, when we had the v coming in this direction, the v0, we showed that we had a force that was either going to go this way or this way, depending upon the charge. And what's the point? Oh, but once you have that force, your velocity is now in a different direction. So this now gives us the capability to account for that and to be able to figure out what's going to happen. So what do we want to do then? We just want to calculate our QV cross B. QV cross B. Okay. And once again, I'm going to do the same thing I did before. I, J, K. This time we have a v0 cosine theta and a v0 sine theta. Sorry, I should have given a little more room there. And just 0 in the z direction. And what do we have for b? B is, sorry, I didn't label it. B is only in the z direction. So we've got some b0 here. So when we calculate that out, we have q. We're going to have a plus v0 b0 sine theta in the I hat. That's going this way. And then we're going to have we're now going in this direction across the terminal, so this is a minus. Sorry, this is just equal to this. Then we have a minus b0 cosine theta in the j hat. Okay, so that's great. This is now our Lorentz force. And actually, just so you guys are aware, I actually don't know if this is just me or if it's other people as well, but the Lorentz force is often written as the sum total of the Coulomb force and the magnetic force. So the Lorentz force will be QE plus QV cross B. It doesn't matter that much what we call it, but the bottom line here is that we are, there is no electric field for this, so that term is 0 anyway. Okay, so now what are we going to do with this? We now have the force. Well, what do we do when we have a force and we want to figure out the motion? We've got to put it in our equation of motion, which you guys all know. I'm going to just make this a little smaller. So we're going to put that in our equation of motion, and that just is MA F equals MA. You guys, fantastic. You guys know that. But we're going to use this definition. We're going to say MV dot, which is just another definition of A, as you guys know, equals F. And so let's go ahead and see what we got here. Well, mv dot, here's v right here, so we're just going to take the time derivative of that. So I'm going to go ahead and give myself some room. So I'm going to do this, yeah. I'm going to give myself some room. All right. So we have, what is v dot? Well, I'm going to go ahead and do mv dot. V dot, let's go ahead and assume v0 is a constant of motion. We can prove that actually very easily because, well, a whole bunch of different ways that we can prove it, but the general way that we can prove it is by recognizing that the magnetic force is always going to be perpendicular to the direction of the velocity. And therefore, we can never do any work on this system to change its energy. So we can't change 1/2 mv squared, therefore whatever our initial v is in magnitude, that's going to be the final v in magnitude. Okay, enough of that. There are other ways to think about that as well, and I can't remember how your book goes about proving it, but conceptually, that's it. Okay, so we're going to say that this is mv0. What is the derivative of cosine theta? Let's see, I always have to think about this. Cosine theta, we start at 0 and we go negative, so it's minus sine theta in the I hat direction. And yeah, I'll go ahead and write out this. And then we have a plus mv0 cosine theta in the j hat direction. And I forgot something that is very important, because what I did here is I took the derivative of this with respect to time, but what I forgot to do is what we're doing here is really this. We're doing dv d theta and then d theta dt. We want the time derivative. And so we need to put a theta dot in here too. So I have theta dot here, and I'm going to go ahead and put it here, but recognize that it's cosine theta times the time derivative of theta. Okay, so this is now our v dot, our mv dot. And what do we know? We know that this equals our f, and therefore it's a vector equation, and we're just going to work with one component at a time. So what do we have? We have minus m v0 sine theta dot equals q v0 b0 sine theta. We're done. So now I just set the two x components of this equation equal, of the f equals ma. I set those two equations equal. And so we can divide both sides by, well, let's divide them by v0 sine theta. v0 sine theta cancels on each side. So what do we end up with? We have theta dot equals q minus qb0 over m, which leads to a solution of theta of t equals q b0 over m times t. What happens with the other equation? Actually, I think I'm going to leave that as an exercise for you guys. And what I'd like you to do is do the same thing I did with this x equation. So I took the I hat terms and equated them. You guys do that for the j hat terms and see what you come up with. Okay, so, oops, and I forgot a minus sign there. Okay. All right, well now, what does this, we now know what our theta is here, so we can go ahead and change our equation here. And so our equation is now cosine of minus q b0 over mt sine minus q b0 over mt. Just substituting in for, I'm going to pop in the I hat and the j hat. Just substituting in for what theta of t is. So now we know what v is. All right. Well, what is our position as a function of time? Well, if we have our velocity as a function of time, we know that, and we're going to break this into, once again, our two components. We'll do x and y. We know that x dot equals v sub x, just by definition, right? So I'm going to go ahead and write this out explicitly, because what we have is dx dt equals v sub x, and we can just go ahead and pop this dt over here, and then we can integrate to get our x as a function of t. And if we do that, we find x as a function of t equals, and here's our x component right here. I'm going to go ahead and get rid of this minus sign in here. Why can I do that? I can do that because cosine is an even function. So the cosine of a negative angle is equal to the cosine of that positive angle. So I can just ignore the minus sign right there. So what do I have? I have x of t equals v0, which is a constant, integral of cosine q b0 over mt dt. And you guys know that this is, let's see, I've got to get this right again. So I believe this is positive, right? So I have v0m q b0 sine of q b0 over m t plus some constant, which I'm just going to call x0. And we determine that by the initial conditions. So there we go. We now know x as a function of t. And once again, I'm going to leave this for you guys to do this exact same thing for the y as a function of t. So just take a minute now and figure out what y as a function of t is. You're just going to do the exact same thing I did, except instead of using this term, you're going to use this term right here. So now we're done. We've got everything that we need. We have x as a function of t, y as a function of t. You've got your velocity. And it's interesting, however, to now look at this. Because what does this mean? What this means, as time goes by, this is going to exhibit cyclic behavior. So this x is going to, if we just look at our x coordinate, we're going to have something that does that. And if we look at our y coordinate, what you guys will discover is you're going to have something that looks like something like this. No, something like this. Okay? And so what does that actually look like? Well, when you look at these x and y's together, you can do this you can do this much more analytically, but you can just look at this and see what happens. Well, what happens? You have an x that's going like this back and forth from one value to another. You have a y that's doing the same thing, but it's offset in time. So what does that look like? It looks like that, which matches our intuition. Because our intuition says that when we have a force that's going, when we have initial velocity that's going like this and a force that's going like that, as we move here, the right-hand rule will say this way, this way, this way. As we move all the way around, it's always going to be a force that moves inward. And it could be inward in this direction, or depending upon the charge, it could be inward in this direction. So, yes. So I've got the charge in there, so you guys see that the direction will depend upon the charge. Okay, I think I'm going to leave it at that for now.